Hello everyone, this is Professor Gant, and this is the third video in the series for Math 109 General Education Mathematics, Module 4 homework assignment. And so these sets, this set of problems will be going over population growth, approximating population growth, and in general compound interest. And before we get started here, I wanted to talk about compound interest and continuously compounded interest and explain why we're actually using the compound interest formula that we're going to use in most of these problems. So whenever we talk about compound interest in general, we have what's called finite compound interest, which is compounding interest based upon a specified number of times per year. I'll go ahead and write that, compounded interest. And so the formula for that is A is equal to P times 1 plus R divided by N. And the 1 plus R divided by N is raised to the power of N times T. Where here we look at A is the accumulated amount, which you can say the new amount. P is the initial amount, and this could be population or money that we're talking about. In terms of money, sometimes this is called the principal, meaning the initial amount that you either invested if you're earning money, or you borrowed if you need to pay back money. R is your annual percentage rate or interest rate. And this number here is always in decimal form whenever we put it into the formula. So for instance, if I said I had an interest rate of 5%, then I would rewrite this as 0.05 when I plug it into this form. N is the number of times, whatever it is that we're talking about, it's compounded per year. And just to be clear, if we say that we are compounding annually, like we're going to see in most of these problems, then N is equal to 1. If we're saying that we want to compound twice a year or semi-annually, then we say that N is 2. If we want to compound quarterly, then of course that would be N is 4. If we wanted to compound monthly, then of course that would end up being that N is equal to 12. And if we wanted to compound daily, then that would mean that N is equal to 365, okay? Now, of course, we could go higher than that if we want, but in most applications, we don't do anything more than doing finite compounded interest daily. So you can do hourly, you can do every second if you want, but really we just keep it, the lowest that we get to is daily. I mean, the highest that we get to is daily, rather. Now, in terms of T is time, and time is always in years unless you're asked to do otherwise, okay? So for instance, if we're given time is equal to 2 years that we have some money that we borrowed and we need to pay back, then of course T would be 2 in that instance. If we had a situation where, let's say, we're only we need to pay back this money in a fraction of a year. So let's say it's 5 months. Then in this case, T would be 5 out of 12, or 5/12, because we know that there are 12 months in a year and we're only spending 5 out of those 12. So in terms of a year, we would say that 5 months is 5/12 of a year. So that's how we would handle that. Now, in knowing all this, whenever we say here that if you see in this problem, it says compound annually, then what that's telling us is that our n here is going to be equal to 1. And if our n is equal to 1, then that means that this value here is 1, and that value there is 1 as well. And I'll go ahead and put the t back there. So this is 1 here, divided by 1 there. And we know that r divided by 1 is just r. 1 times t is t. So here, this would end up simplifying to this particular equation here. And you see, for most of these problems, this is the formula that we're going to use because we will be told to compound annually, which means that our n here, the number of times compounded per year, would just be 1. Okay. Now, on another note, going to go ahead and go to another page here. We also have what's called continuously compounded interest. And continuously compounded interest is just basically interest when n approaches infinity. Okay. And so if we were to use this particular formula here and say as n approaches infinity, what it would turn out to be is that this formula would end up being a is equal to p times e raised to the rt, or p raised to the p times e raised to the rt, where e is an irrational number that's approximately equal to 2.71 that shows up a lot in anything that exponentially grows or exponentially decays. So my point here is that if we were to get higher and higher on saying the number of times we compound money, or if we could say that, hey, we have continuously compounding interest on something like a population, and we're saying that at every moment of every day, it's sort of increasing or growing upon itself, then this is what the formula would end up being. And how this changes into the finite compounded interest formula changes into this other formula here. You actually learn that in a first year calculus course. No need to go over it here since this is not a calculus course. I'm just letting you know that that's how this formula turns into that. Okay. And so we won't be using this problem or this particular formula much here in this homework. And the reason is that they're wanting you to do all of your calculations by using this simplified compound interest formula. Okay. And even when they ask for population growth type of problems, which you're going to see here, traditionally, those type problems are answered using this formula. But for purposes of what we do in this course, we're going to use this one to do that. So I wanted to mention that just in case you may go and use some other resources or whatnot. And let's say you're trying to do population growth type problems, and you start to see them using this particular formula here. That's the reason why, because if we want to figure out what the exact growth is or whatnot, we use this formula. The one that we're going to be using, we're going to be approximating, let's say, population growth by using this finite compound interest formula. So I wanted to make sure that that was known before we get into all the calculations here. Now, with that being said, I'll go ahead and erase, and then we'll start working this problem. And just to let you know, the problems that we are going to work in this particular section or this particular video will be number 9, number 10, number 12, number 30, and number 31. Okay, so these will be the problems that relate to compound interest, annually compounded interest and population growth. All right, so got all that erased, and now let's go ahead and do this problem. And so we're given that the principal in a bank at the beginning of a year and the rate of interest that is compounded annually. We're given that information. We want to calculate the amount in the account at the end of the year, meaning we want the accumulated amount. So here we're using this formula here, and we know that our P is going to be $6,000. Our interest rate is 6%, so 6% written in decimal form is 0.06. The time that they gave us is 1 year, okay? And so we have all the information that we need. So therefore, A, which is going to be the new or accumulated amount in the account after the first year, is just going to be 6,000 times 1 plus 0.06 raised to the 1, okay? And of course, this is just 6,000, and this being raised to the 1, anything raised to the 1 is just itself. And 1 plus 0.06 is just 1.06. Of course, if we go ahead and multiply that together, that's just 6% more than 6,000. And we will get $6,360. And so this is what this amount should be. All right, so we'll go ahead and move on to number 10. So for this particular problem, it's pretty much the same thing. The only thing that's different now is that we're changing the numbers. We're giving principal at a bank, rate of interest compounded annually. Instead of having 6,000, now we have 9,000. And instead of having 6%, we have 8%. So pretty much the same. I'll just change these numbers, and we will do the same thing that we did last time. So 9,000, 8%. And here, just change this. So here, 9,000, 9,000, 9,000, 8%, 8%, 8%. And so all we need to do now is figure out what this new number will be. And of course, if we take 9,000 and multiply it times 1.08, we get $9,720. And that's our accumulated amount here. And notice that these are exact numbers, so there's no need for us to actually round to the nearest cent here, because these are the exact numbers. All right, let's move on to number 12. All right, so for this question, it says you are given the population and the growth rate as of 2004 for a country, and that's the year 2004. Assume that the growth rate remains the same from year to year. And of course, our growth rate here is 1.1%. Use an exponential function to model population growth and determine the size of the population in the specific year. Okay. So here, we're told that we have some population growth, and we start off with 1,035 million, which is, if we translate that, that's going to be 1,035,000,000 people. So, but we'll just keep it as P is, we'll keep it in thousands here because our units here is million. Our growth rate which is R, that will be 1.1%. So if we take 1.1% and translate that in a decimal form, it is 0.011. And we're told that the year is going to be 2013. Okay. Now, whenever we use this formula here, the understanding is that this P here, which is the initial amount, which is going to be our population here, is starting at some particular point in time, which is 2004. So here we know that this is going to be the time when T, well, this is going to be the population when T is equal to 0. So here to figure out what our actual time is going to be in years, we need to do the difference in between 2013 and 2004. Okay, and of course the difference in between that is 9. So we got all of our information here. So now we can just plug in, put in 1035 for P, 1 plus, we put in 0.011 for R, and then for T, we put a 9, okay? And so now what we could do to calculate this, of course, I'll go ahead and simplify this part in the parentheses. This is 1.011, all that raised to the 9. And if you have a graphic calculator, you could type in this result this way. I'll move this over so that we can calculate it. So here we want to take this 1035 times 1.011, raise that to the 9. So if you have a graphing calculator, you can just do this directly. Do parentheses and then 1.011, close parentheses. And we use this button to raise to the exponent, do 9, and we get this amount here. So the population of 1,035 million people will increase to 1,142 people and some change. Okay. Now, if you do not have a graphing calculator, and you can't type it into whatever calculator you're using like this, then what I'm going to suggest that you do is do this in pieces. Okay. And so according to order of operation, we have to do exponents before we do multiplication. So if you're trying to calculate this without having a graphing calculator that will allow you to type everything in, then what you need to do first is this. I'm going to clear this. We need to do 1.011 because that's what's in the parentheses. And of course, exponents come before multiplication. So we're going to raise this to the 9. And for those of you that have, let's say you're using a calculator on your phone, you may have something that looks like, now get rid of this for a second. It may look like a button that says Y raised to the X or something like that. Or you may have this particular button on your phone or whatever calculator that you're using. I think sometimes they look like this as well. So, but regardless of what it is, you need to find out what the raise to or exponent button is on your calculator and use it. So I'm going to get rid of this and we're going to finish this now. All right, so once we're here, we'll go ahead and enter in this answer. So we get this amount. And so that's what this 1.011 raised to 9 is. And then we just multiply that by 1,035. And we see that we ended up getting the same thing. So the number that we got here is 1,142.091108. And if we're rounding to the nearest tenth, in this case, we'll round to the first decimal place. Then this is going to be 1,142.1 million. All right. So this problem is done. The next thing that we'll do is move on to number 30. All right, so for our next question, it says a bank account has an initial deposit of $16,000. Okay, so initial means P, so that's going to be $16,000. So after 6 years, so we know that the time is 6 years, the bank account has 29,000 in it, which means the accumulated or the new amount is this much. Assuming that compounding interest is done annually, which means our N is 1, and that no withdrawals are taken out, find the annual interest rate on the investment. Okay, so this problem is a little different. We're still going to use this formula here. Okay, and of course, note that this originally had a divide by n under the r and an n times t here, but since n is 1, that's taken care of and it simplifies to this. So this part we'll get rid of. And here, the one thing that we don't know is what r is. So we need to figure that out. So we know that our accumulated amount after 6 years is 29,000. The initial amount is 16,000. R is what we need to solve for because that's the interest rate. And T here is going to be 6. So when we go to solve for R here, note that, again, order of operations is important here, okay? Now, if we knew what R was, we would do everything inside the parentheses here, which is add 1 to whatever R was, raise it to the power of 6, and then multiply it times this value, okay? Since we're solving for R, we need to get R by itself. And so since this particular expression here, 1 plus R, all that raised to the 6, is being multiplied times 16,000, the first thing that we can do is divide both sides by 16,000, okay? And when we do that, 16,000 divided by itself is just 1, and we just have 1 plus R, all that raised to the 6. On this side, of course, we have a common factor of 1,000 with the numerator and denominator. So this fraction just simplifies to 29 over 16. So from here, again, we need to get R by itself. And to do that, we have to get rid of the 6 somehow. And so remember that this is some number raised to the 6. So how we would get rid of this is to take the 6th root of both sides, okay? Now, if that doesn't make sense to you, let me come down here right quick. And let's say if I asked you to solve an equation like this. And so we've seen this before whenever we did the quadratic stuff. So here, if I asked you to solve this, then of course we talked about doing the principal root. And when we did that, of course, I told you to do plus or minus because we know that we have solutions that are both positive and negative. But remember how we took the square root of everything that was on that one side, and then the other side we just let be this, okay? So my point here is that whenever we take the square root, that's like taking root index 2, okay? And so here, what we're going to do up here is instead of taking root index 2, we're going to take root index 6. And on this side, this would just be 1 plus R. Now, here we know that this should be plus or minus because this is an even power again, just like this is an even power. But we're going to see that once we work all this out, the negative part is really not going to make a whole lot of sense, okay? So I'm going to erase this and we'll go ahead and finish the problem now. So now to get R by itself, the last thing that we need to do is subtract 1 from both sides. And that goes to 0. We just get r. And this is a -1 plus or minus 6th root of 29 over 16. Okay. Now, what this means is that either you have -1 minus 6th root of 29 over 16, or you have -1 plus 6th root of 29 over 16. And of course, having a negative interest rate here does not make any sense. So that's why that answer does not make sense. Okay. Now, what we do need to do at this point is figure out, well, how do we put -1 plus 6 root of 29 over 16 into our calculator. Okay. I'm going to show you a couple of different ways to do this. So I'm going to go to next page here, and so here I'm going to rewrite this -1 plus 6 root of 29 over 16. All right, so one translation of 6 root, and we know this because whenever we deal with things that have fractional exponents, that is like us saying the nth root of x raised to the m. Okay. So in this sense, whenever we say this, this is like us saying we have it in this form where this 6th root, this is like 29 over 16 raised to the 1. If we took this and put it in this form, this would be like saying 29 divided by 16 and all that raised to the 1/6 power. Okay, so that is one way that you can do this. And for those of you who do not have graphing calculators, this will be the way that you need to do it. Okay, so that's why I'm doing it this way first. Now, how do we actually put that in? Okay, so I'm going to come back here and let me move this over. All right, so here we have -1, and then we do plus, and then I'm going to do my parenthesis, 29 divided by 16, close parenthesis, and then here this is the raised to, and then I'm going to do 1 divided by 6, so 1 divided by 6. And I do that, and that will be the answer that I get. And what we'll do is change this into percentage rate by just multiplying times 100. And so our answer will be 10.4196, and they'll tell us how to round. Okay. If you do not have a graphing calculator, then what you need to do is calculate this part first, the 29 over 16 raised to the 1/6. So here, what you need to do is to type it this way. You need to say parenthesis 29 divided by 16, close parenthesis, and then after that, find whatever button that tells you to put things in the exponent. And then here, depending upon how your calculator works, I would suggest that you do parenthesis and then do 1 divided by 6, close parenthesis. Okay, and then after that, hit enter, and you'll see that you have this value. And then all we have to do is add a -1 to it, or subtract 1. And you'll see that we get the same thing as we got up here. Okay. So, and of course, if we multiply this times 100, then we'll get this 10.419, so on and so forth. So, regardless of how you look at it, you'll see that that answer is roughly about 10.4%. Okay. So, I'll go ahead and write out all the numbers, and then we'll round. So this is 0.4196 for 4229. And of course, this is the same as saying 10.4196422, this percent. Because, of course, we have to multiply that times 100. And if we round to what is it, the hundredths place, so that's 2 decimal places, then this should be 10.42%. So here, since this is in percent form, we have to write this as 10.42. All right. So our last problem will be number 31, which will be our next question. All right, so our last question for this video is similar to some of the problems that we had towards the beginning of this, where we're given a certain population amount, growth rate, and we're given a particular year, and from the year we have to figure out what the time is. So that's what's going to be different here. So again, we are using this particular formula. Oops, forgot we're not using the n here. All right, and so here we know that our initial population is 156 million. The growth rate, R, is 1.358%. So that means in decimal form, it's going to be 0.01358. And of course, for our time, the year is 2027, but we actually started measuring this country's population and growth in 2011. So we have to do the difference in between 2027 and 2011. And of course, that will end up being 16. So basically 16 years. So now it says the size of the population in 2027 will be about, and we'll go ahead and just plug in everything. So here the only thing that we don't have is A, so that's what we're looking for. So we do the 156, 1 plus 0.01358, and all that's raised to the 16. Of course, 1 plus this decimal number here is just 1.01358 raised to the 16. And then we'll just bring our calculator in and do the calculations for this. So I'll do this as if I didn't have a graphing calculator first. I'll do 1.01358. That will be raised to the 16 power. Get that amount, and then we multiply that times 156. And that will give us 193.5767158. So I'll go ahead and write that down. So 193.576.158. And we need to round this to the nearest hundredth place. So that means 2 decimal places. So it's 7, so 6 is larger than or equal to 5. So this will round out to 0.58. And that should be an approximation sign there. So here this will be 193.58 million people. That will be the projected population in the year 2027. All right, so with that being said, that concludes this video on population growth and compound interest. I will have another set of videos for you here. If you've watched these in order, then the next video that I will do will be on equations of variation. And then the last video will be on geometry. And of course, in geometry, we'll be covering complementary and supplementary angles, similar shapes, calculations for a polygon as far as angles are concerned, and we'll talk about some area and Pythagoras theorem as well. So we'll go ahead and end this one, and I hope you tune in to the next one with equations of variations.